Now let us do a numerical on de Broglie's dual behavior of matter. The numerical is find the wavelength associated with the electron moving with the velocity of 2 into 10 to the power 6 meters per second. Now, so we are supposed to find out the wavelength which will be associated with a moving electron, which is having the mass of electron, we know already 9.1 into 10 to the power minus 31 kg, and we also know it has been given the velocity is 2 into 10 to the power 6. So we know lambda is h over mv, so it will be 6.626 into 10 to the power minus 34. The mass is 9.1 into 10 to the power minus 31, and velocity is 2 into 10 to the power 6. So when we solve all this, what we get is 9.6 into 10 to the power minus 10 meters. Now this is the wavelength which is we find is associated with the electron. Now though again this wavelength seems to be very small, but it is very much significant, particularly when we see the size of the atom. We know that size of the atom is usually lying in the range of the 10 to the power minus 10 meters or 1 Armstrong's unit. So in comparison to the size of the atom, this is very much significant. Whereas if we try to find out the same type of wavelength associated with a moving ball of any particular mass, like a cricket ball or a tennis ball which has a mass in some grams, we will always find that this wavelength will be very, very small, which will be almost of insignificant value. So that is why we always see that these particles moving straight wave particle like, they are not showing any wave like motion, because the wavelengths associated with such cases are very, very small.